Hey guys, today I'm going to be showing you a quick proof of the product rule, which is a rule in calculus that says that the derivative of the product of two functions f and g of x is equal to f of x times the derivative of g of x plus g of x times the derivative of f of x. Now to prove this, we first need to remember the limit definition of a derivative, which says that the derivative of a function f of x is equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. Now what this is basically a way of finding the slope between these 2 points, f of x plus h and f of x. If you look at this graph here, which is the graph of f of x, you can see that if we take these two x values, x and x plus h, and find their respective y values, that this becomes the slope formula. If we add and subtract x from this denominator here, you can group these together and see that this is the slope formula for the slope between these 2 points. And so what we're doing by taking the limit as h goes to 0 of this equation is we're finding the slope of this line as these 2 points get closer and closer together, which will eventually approach this tangent line, which is the derivative that we're looking for. So now, in order to prove that this product rule is true, we're going to use the limit definition of a derivative, but plugging in this product rule instead of just regular f of x. Okay, so I'm going to write our derivative over here, which is the derivative of f of x times g of x. And we know that this equals, according to the limit definition of a derivative, f of x plus h times g of x plus h minus f of x times g of x all over h. This is just the limit definition, but instead of f of x, we just plugged in f of x times g of x. Now, at this point, we can't really do anything with this function because these are 4 different variables and they can't be combined. But what we can do is add something else to this fraction so that we can separate things out and end up with these 2 terms here. So what I'm going to add here is a plus f of x times g of x plus h and a minus f of x times g of x plus h. Notice that these 2 terms here cancel out because they're exactly the same. It's a plus and a minus. So we actually haven't added anything to this equation, it's just plus 0. But what this lets us do in the numerator now is we can rearrange these terms and then group them into 2 separate fractions, which we can solve. So first I have this term here and this term over here. These terms both have a g of x plus h in them, so I want to combine these over on this side. So if I rewrite our limit here, and this is all still over h. We haven't changed the denominator at all. It is exactly the same as it originally was. Now, these other 2 terms both have an f of x in them, so I want to combine these on the other side of this fraction. Now that I have my 4 terms like this, I can split this into 2 separate fractions that both have h as the denominator. Now notice that the only thing that I've done is added these 2 terms, which cancel out. So this limit is still exactly the same value as it originally was. I need to do one last thing in order to be able to solve this, and that is I need to factor out the things that I originally grouped these terms by. So over here, both of these terms have a g of x plus h in them. You can see here in orange. And then on this side, both of these terms have an f of x, and that shows up in purple. And so that means that I can take these out of the fraction and move them to the front. So now I have the limit as h approaches 0 of g of x plus h, which is our factor that we just pulled out, times f of x plus h minus f of x all over h. This is the fraction that's left. Notice that we've separated the g and f of x completely. Now on this side, we can separate out our factor of f of x. So that's here. And then what's left inside the fraction is g of x plus h minus g of x all over h. And so that is our final fraction that we have. Now this limit here is still equal to the original. It hasn't changed at all. It has the exact same value, but it is a lot easier to evaluate in terms of g of x and f of x. So if you remember, when we have a limit of a product like this, if we have a limit as h approaches 0 or really anything of f of h times g of h, we can separate these two, take the limit of each of them, and then multiply them back together. And this will give us the exact same thing. This is one of the properties of limits. And so with this in mind, we can solve this all in one step. So the limit as h approaches 0 of this here is going to be the limit of this times the limit of this. Now the limit of g of x plus h as h goes to 0 is just going to be g of x, because as h goes to 0, this is going to be g of x plus 0, which is just g of x. Now this, you may notice, is exactly the same as our limit definition of a derivative. So this can be solved as derivative of f of x. So this is our first term. Now for our second term, I'm going to bring this plus sign down, and f of x as h goes to 0 is going to just be f of x, because h doesn't even affect this at all. So this is still f of x. And this last term here, you may notice, is the limit definition of the derivative again, except this time it's with g of x. So this is the derivative of g of x. And this is the evaluated limit. This is the final form. And as you can see, it is exactly what our product rule tells us. In this case, it's backwards, but you can flip these two terms around and get the exact same thing. So this is the proof of the product rule in calculus. Thanks for watching. Hey guys, thanks for watching this video. If you enjoyed it, please be sure to like, comment, and share with your friends. If you want to help support my channel, you can click the circular icon to subscribe and turn on notifications to see whenever I make new content. Also, you can check out some of my other work shown here by clicking the links in the video. If you're currently struggling with math, please let me know what topics you're having trouble with, and I can explain them in the next video. Once again, thanks for watching, and see you next time.